Okay. Hello, everyone. Welcome to this session. So for those I haven't met yet, I'm Kedar Namjoshi, student of Alan's. I work at Bell Labs, where I've been there ever since I graduated. It's been a long time. So today's first speaker is Ken McMillan. You've already heard about him and the work that he does, so I'll keep it short. So Ken is really one of those major people who are responsible for the growth and development of model checking as a practical tool. But I've always admired his work and like the elegance of his methods, as well as the impressive results that he gets. So also, just like there are families, there are academic families. So Ken is an academic brother, I guess, of Alan's, as is Prasad. So you'll see more of this family, in this session. So with that, Ken, over to you.
Thank you. Thank you, Kedar. All right. So what I'd like to do in this talk, just briefly, is to trace the evolution of the idea of model checking seen not as a technique, but rather as a research paradigm, right? And a research paradigm that I've sort of worked in most of my career. So you're probably familiar with the idea of Thomas Kuhn, of a paradigm as a set of problems and a set of strategies for solving those problems that are common to a scientific community, right? And of course, a paradigm is also an element that represents a whole, or an example that represents a class. So what I'd like to do here is consider model checking as a paradigm and think about what are the fundamental unresolved problems in that paradigm, and what are the common strategies that we use, because I think it's interesting to think about the evolution of a very simple idea into a very complex paradigm. Okay. So, all right, thinking about, in the first place, what problem are we trying to solve in model checking? Well, this is a problem that, of course, goes back to the early days of programming in the 1940s, maybe, where people observed that programming is a very unreliable process. Right? And so the most obvious thing that you would think to do in that case, if you thought about it for a minute, would be to say, well, let's use some logic and let's prove the correctness of the programs. But initially, it was a research topic in and of itself, just to capture or abstract the semantics of programs into logics, right? So we have, initially people like Floyd and Hoare and Dijkstra that are thinking about, capturing the logical semantics, sort of the big step semantics of the programs. And we get more refined with Pinwelly's idea of using temporal logic, where we can think about, the infinite sequences of small steps of non-terminating programs. And we're getting to the point there where we can now state the proof problem, but we still have the problem that proofs are really hard. Right? And a lot of people at that time, some very prominent people back at that time, were very skeptical that we would ever be able to carry out those proofs, which is why I think it's quite remarkable that a few years later you have Clark and Emerson and Safakis coming along and saying, no, well, for a certain class of programs, the proofs are free. You just push the button and you get the proof automatically, which is remarkable. And it creates a paradigm, and the paradigmatic problem is, of course, CTL model checking, right? Where we have this finite state graph that's labeled with some propositions, and we have a specification that's written in this very simple logic, CTL. Here I've said, always if P is true, then always eventually Q is true. And now we just want to say, is that graph a model of the formula? And lo and behold, that problem can be solved in polynomial time with an algorithm that essentially just exploits the fixed point characterization of the logic, which is wonderful. But of course, if you were a skeptic, and others have pointed this out today, you might object that programs are not, in fact, finite state, or not very many of the programs. So why should I actually care about this? Right? Well, okay. But if you look a little deeper, in that 1981 paper on synchronization skeletons, you see that the idea wasn't really, of course, to verify finite state programs. So the paradigm here is this. We're going to define a program model and a logic such that we have tractable verification, okay? And then we have to reduce our verification problem into that framework. It's not going to be a finite state program. We have to somehow make it a finite state program. So we'll start with some program M, not finite state, and some formula phi, not in CTL, or some specification, however you write it. Right? And we're going to say reduce that program M into an M prime that is finite state, and reduce our specification, whatever it is, into CTL. And that finite model is going to be some kind of an abstraction. Right? For example, in that original paper, Alan was thinking about the abstraction as being a synchronization skeleton that essentially extracted out just the finite state concurrency control part of the program. Okay? So this is a nice, elegant view of reduction. You take a problem you don't know how to solve and you reduce it to a problem we do know how to solve, which is, of course, very familiar. But there is a slight issue here, which is that, of course, we still need this proof that says if the finite state model is correct, that the original program is correct. And maybe in the case of a synchronization skeleton, that would be quite easy to do, right? Because those two programs are very closely related. But if this extra proof that we have to do is harder than the original proof, then we haven't really gained anything in the reduction. And this part is sometimes what I call the latent proof cost. That's the proof cost that we model checking people tend to sweep under the rug and ignore. Okay, but certainly Alan was aware of this, right? That you had this problem of the reduction. So, and we'll talk more about that later. Okay, so what I would say is this. I think model checking was a very good idea that solved a very specific problem. But there was a great idea in that paper, right, which was that proof problems of low complexity could be hiding in proof problems of high complexity. And we just have to find those problems. And then we can treat the problem of proof as a problem of reducing one problem to another, just as we always do in computing. Okay, so that's the big idea to me, not model checking per se, not CTL per se, right? Although CTL was an example of that approach. Okay, so of course, every solution creates new problems, right? And I would say this, a good idea solves a problem, but a great idea creates a new space of problems for other people to solve. And to me, that's what Alan's idea of model checking actually does, right? So, and why is that? Why does it create new problems? Well, because there are inherent tensions within this paradigm of reduction. Okay, and in particular, to succeed in this process, we have to satisfy a number of criteria, right? And I would identify 5. And the first 2 of those have to do with expressiveness. So I need a model that's sufficiently expressive, and I need a specification formalism that's sufficiently expressive such that there exists a simple reduction from the problem that I want to solve into the problem that I can solve. Right? I can always take any safety property and reduce it to a state machine with 2 states, one good state and one bad state, but it doesn't help me in the proof because it eliminates none of that latent proof cost. So we need expressiveness to do that. Also, we need to scale. So it's not going to work if we take a tiny problem and reduce it to a huge problem in a different framework, right? And this is very important. And of course, implicit in this paradigm is that in the reduced problem, we have to have proofs at low complexity. Right? We need to be able to prove that we have correctness of the abstraction in, say, polynomial time. And we have to have counterexamples at low complexity, right? Because we're humans, and almost all the time when we try to prove something, we're wrong. Okay? It's actually false. So counterexamples are just as important as proofs. And what we find when we try to do this in practice is that these 5 conditions are tightly related and very hard to satisfy at the same time. All right? So in other words, it introduces what I call the game of model checking whack-a-mole. You push in here, and it pops out there. So let's think about a few cases. Suppose I want to verify sequential circuits. Well, if I reduce the sequential circuit to a Kripke structure, that's exponential. Right? Or another way of thinking about it is if I use the sequential circuit as a model, then my lovely CTL model checking problem is now p-space complete, right? Instead of being polynomial, right? So I tried to push in on expressiveness and it popped out in complexity, okay? Or, right, and basically all of these problems I'm going to talk about are things that Alan worked with his students or that his students worked on. So, or let's say that instead of talking about one process, I want to talk about an arbitrary number of finite state processes interacting with each other, which is, of course, famously an undecidable problem, the parameterized model checking problem. So again, here I've tried to push in on expressiveness and it popped out as undecidability. Right? Or let's say I just want to improve the expressiveness of the logic, moving from CTL to CTL star, right? Again, we come out with higher complexity as a result. And yet, it might be very tricky to reduce our problem into the weaker logic CTL. Okay, so those are just some examples of the tensions between these different requirements that we have for expressiveness, scaling, and algorithmic proof. Okay, so as a result of those tensions then, what you start to see very soon is the development of research strategies, right? We have an unsolved problem, and now, or space of problems, and now we have a set of strategies to go about trying to solve them, right? And here are a few that I'm going to talk about that I think are almost complete. Okay, so one is we're going to say, well, this problem might be hard, but practical instances of it have some structure that I can exploit to solve it in practice. So that's one class of strategies, right? Another class is to say, well, if I try to extend the expressiveness to, say, handle many processes, I may find it's undecidable, but I can put some cute restrictions on the model that will prevent us from crossing the line into undecidability. So that's restricting the model. Okay. Another one is we could say relax the criteria. For example, we could give up on counterexamples or give up on proofs. Right? This is very common. And the fourth one is to say, well, I'll really give up on the idea of automation, maybe because I don't entirely get automation in the first place, and I'll try to collaborate with a human to construct a proof. Okay. So if you look at any paper in model checking, almost all of them are going to be using one or more of these 4 strategies to try to play the model checking whack-a-mole game and to get a practical technique for doing some real verification. So I'll just talk about a few examples of those cases, and again, we'll see lots of things that Alan worked on, or that Alan worked on with his students. Okay. So as I said, the exploiting structure strategy says this problem is hard, but practical instances have structure, right? So you can see that, for example, in symbolic model checking using BDDs, right? You can see that in symmetry reductions, right, that Alan worked on. You can see that in partial order techniques. So we can exploit symmetries, we can exploit the fact that operations commute with each other to try to reduce the complexity of this problem. Not really reduce the complexity, but solve practical instances. Right. So what that means usually is we're trying to come up with some clever algorithm that will operate on some reduced form of the problem. And so it's really kind of a direct attack on the complexity or the scaling issue algorithmically. And of course, there are limitations to this kind of thing. Okay, so the second strategy that's really common is what I called model restriction. So the idea here is, let's say that we want to have parameterized processes, but we find we run into this result about undecidability, so we try to restrict the model. For example, in broadcast protocols, you're restricting the communication between the processes and in a way that tries to get around the undecidability. And maybe when you do that, you can say verify cache coherence protocols or some particular class of system that fits that restriction. And of course, you can come up with lots and lots of restrictions because no one of these is going to cover a large class of systems, and people do. So you can see the same idea working in timed automata or working in well-structured transition systems, Petri nets and so forth. So this is a really common strategy for trying to, again, work out these difficult compromises in model checking. Okay, third strategy that I mentioned, relaxing the criteria. This is probably the most popular strategy of all, right? Is to say we're going to give up on one of those 5 conditions and hope that we still have, in some way, a practical technique. So, for example, bounded model checking is, of course, sort of the paradigmatic example of that, where we're saying we're just going to do bug finding, and give up on proofs, but by doing that, we'll be able to scale a little bit more. And this is, of course, maybe the most popular formal verification technique in hardware. We can run down a long list of such things, concolic testing, context-bounded verification, and so forth. Giving up on free proofs, which sounds terrible, but counterexamples are still valuable. Right? Or we could give up on really proving the specification that we want and restrict ourselves to very shallow properties. And that way we're giving up on our expressiveness of the properties, but then we can use a lot of relaxation methods like counterexample guided abstraction refinement or interpolation or IC3 and so forth. So we have a huge number of algorithms that are basically trying to prove very shallow properties of rather complex systems, again, giving up here in order to get something there, right? Or, we could go in the other direction and say we give up on counterexamples. So techniques that are using abstract interpretation, techniques that are using, template invariants and things like that can give us proofs, but they can't give us counterexamples, right? And finally, there's a huge class of techniques that just gives up on specifications altogether. Like, for example, angelic verification, or maybe you could think of equivalence verification in that class, which sounds strange, and yet, these are still possibly practical techniques, and people are working on all these different angles, right, to try to work around this fundamental tension in this basic technique of reduction. Okay, so, all right. And of course, strategy 4, collaborating with humans. This is the one that I think is really the only one that ultimately will give us scale, right? And this is basically saying, we're just not going to do the proof automatically. Humans are going to give us abstractions. Humans are going to give us decompositions of the problem into lemmas that we can solve automatically and so forth. So again, a huge class of strategies, all the various compositional techniques that are taking input from humans would fall into this class. And, of course, the difficulty there is it's humans doing proofs, and proofs give humans a headache, right? So this might not be popular, but in a way, it's sort of the only thing that I think really ultimately scales. So the point that I'd like to make here, right, is about this very simple idea of model checking and how it ramifies into a very complex research area with an extremely rich literature that's kind of hard to get your hands around, right? So in other words, a great idea creates a new space of problems by containing a fundamental tension, right? And that space of problems creates a research paradigm, and the research paradigm creates careers for people like me, for example. So what I tried to look at was just a brief view of this set of strategies and how they fit together, right? And give an idea of how remarkably productive this model checking paradigm has been over the decades. And if you look at those basic strategies, they were all more or less in place by about 1990, but they've been sort of ramifying and being developed and made more complex, so forth, for about 45 years now since that original paper. So, just to conclude, very few scientists have the distinction of seeding a new research paradigm as prolific as the model checking paradigm has been. And that's truly remarkable, right? And I think that says something remarkable, though I don't understand it, right, about the insight that went into solving that particular problem, or perhaps not solving that particular problem, which is maybe the point. So perhaps the rest of us can be inspired, right, by the way Alan thought, right, to not solve the problem that will lead to the research paradigm and verification for the next 45 years. Thank you.
Thanks, Ken, for a wonderful talk. I think you've just given us the recipe for how to write the next 100 papers or whatever.
Should I take my laptop?
Oh, maybe, I mean, you can leave it up, but maybe I think it's going to come from the Zoom anyway. Yeah, okay. So the next speaker, do we have David Dill on? Yeah, so the next speaker is David Dill, who's an emeritus professor of computer science at Stanford University. So like Ken, David has been instrumental and central to building up model checking and more generally verification as a practical tool with really good insights into and tools that come out of those insights into topics as diverse as microprocessor verification, decision procedures, and more recently on the verification of neural networks. So David, there you are. Okay, take it away.
I'm thrilled to be here, although I'm not, it's unfortunate that we have this occasion. I was disturbed to see that Alan was only 3 years older than I am, even though I regarded him as being senior because he finished his PhD much earlier than I did, and I always looked up to him as my older advisor sibling. For this talk, I don't have a lot of mathematical content, and I have 2 unimportant slides that I will attempt to share if it's not too much trouble, if it works very smoothly at the end of the talk. Otherwise, I'm just going to talk about what Alan's work, the impact that Alan and his work had on me. So I'll also give my own history, which may or may not resemble actual factual history, but it's my perception of how things went in the world. So let's see, model checking was really the right idea at the right time. I think that's part of the reason that it was successful. And formal verification, as we've heard, is of course a classical topic in computer science that was worked on for decades and before model checking hit the scene, and was responsible for there were some very leading researchers working on it. So I learned about formal verification in graduate exams at Carnegie Mellon. But at the time, I was interested in compilers and compiler optimization. And I never really liked formal verification as a topic. It seemed hopelessly impractical. We were asked to read long papers, which were long and complex. The punchline was developing a new technique for verifying some sort of 5-line toy program. And I learned later that the reality was that that whole style of verification and the field was undergoing a winter period after some initial enthusiasm where funding agencies funded a bunch of work and then became impatient and disillusioned, even though in retrospect that work turned out to be quite important to the development of the field. But sometimes funding agencies don't have the patience that they should have. Alan's development and Ed Clark's development of CTL model checking in 1981 was the right idea to basically rebuild formal methods from the ashes, because it was a fully automatic technique that, when it worked by brute force. And so it got around many of the problems that the previous methods had, which was inadequate theorem provers and lots of manual effort. So at the time, it opened up new opportunities. Although I must say, it was quite a long, difficult journey to legitimize the topic. As we heard, new conferences had to be started, et cetera, to even get a place to publish. So after a checkered history at Carnegie Mellon, I became Ed Clark's student in either late 1983 or early 1984. And in retrospect, I was definitely a troubled student. I think he took a risk on taking me. He had transferred to CMU from Harvard after, I think, 5 years at Harvard. And I was his second student at Carnegie Mellon. So maybe I was lucky that he needed students at that time, another case of being in the right place at the right time. So I messed around for a while trying to do compiler work or something. Finally, Ed handed me a bunch of his and Alan's papers to learn from and suggested I look at the problem of verifying self-time circuits. So self-time circuits are the smallest concurrent system with bugs, and it was entirely Ed's idea to pursue those. He had already sought out contacts with experts in self-time systems and just pointed me in that general direction. So there was a primitive CTL model checker written in Lisp that worked for, I think, up to 10,000 states, I guess, after I hand optimized it. And I started translating circuits, speed independent circuits, to Kripke structures and working on those things. And I found, contrary to my previous 3.5 years at Carnegie Mellon, that I was getting publishable results very quickly. So it basically created my career in research. So I found the papers difficult to read, but they were clearly written, and I was able to learn what I needed to. And during this time, I happened to meet Alan because he had recently finished his PhD and would visit Carnegie Mellon and add occasionally to work on research. So I would get a chance to talk to him. In retrospect, I was pretty immature, and I only knew a tiny fraction of what he did about logic and math. This is actually still true. But Alan was patient and happy to talk to me, answered all my questions, and explained things in terms I could understand, and he was unfailingly kind. So I continued working on my PhD and for another, I think, 6 years, and eventually got it to the point where the end was in sight. And so in 1987, in the winter and spring, I started interviewing. And it was partly the example of, or primarily, I guess, the example of Ed Clark and his students, including Alan, that made me think that maybe I wanted an academic career instead of an industrial career. So I went on the interview trail, and I was pleased to get an interview at the University of Texas with Alan as my host there. While I was there, I gave a well-attended talk on my PhD thesis work. I got to the future work section, and I was talking about my hope of verifying systems with timing when I heard from the back of the room someone saying loudly, "Yuck." There was a deathly silence that fell over the room. I looked around and I saw various people staring at their feet and shuffling them uncomfortably. I said, "Did I hear a yuck?" This editorial comment had come from Edgar Dijkstra, who, for a PhD student like myself, had near godlike status. So, given that I had just seen my hoped for job offer go up in smoke, I was liberated so I could speak my mind. And so I calmly argued that taking timing into account might not be a completely stupid idea. And then we moved on to other questions. After my talk, Alan was the first to congratulate me on standing up to Dijkstra and told me that Dijkstra had a reputation for being blunt and assured me that not all was lost. So I felt better and continued with my interviews. While I was there, truly amazing thing happened, and this was probably the biggest impact that Alan had on my career. I had been working on a thesis problem for a long time, and I think actually it took me 2.5 years to finish my PhD thesis, and I must have spent a year distributed over that time messing around with this problem because it seemed like it should be simple, but I just couldn't solve it. And so when I was on the interview trail, I would explain that problem to people who might be able to help. I didn't think they understood. I don't think they understood what I was talking about, and no one had useful suggestions. except for Alan. So I explained the problem, expecting the usual blank look from him. He stroked his beard in the usual way and then said, I think there's something relevant in a book that was translated from Russian by Trachtenbrot and Barsden. I think Larry Landweber was reviewing an English translation, and then he noticed that one of the proofs was wrong, so he corrected the proof in the English version of this book. So I took notes on this. I'd never heard of this book. And when I was done interviewing, I looked it up. And sure enough, there was a chapter that was closely related to my thesis problem. I never fully understood the problem in the book, but I was able to reduce my problem to their problem and solve it. And it went into my thesis. So I spent a few weeks writing up the solution and then declared victory on my thesis and was able to leave that problem behind and get on with my life, basically. I did get an offer from the University of Texas, to my surprise, and I seriously considered it, in part because of Alan's presence there. I eventually decided to accept an offer from Stanford and then stayed there for 30 years. Um, After I got a faculty position, I interacted with Alan several times. He was my host at the University of Texas, and he was an editor at a journal who guided one of our papers through publication, requiring basically a complete rewrite. I think Richard Truffler did the heavyweight reviewing on that paper, and I was grateful for both of their efforts. So I will now attempt to share the slides, my two slides, and we'll see if I can get this to work quickly. Okay. So here is the slide that I did quickly, as well as I could remember it. This was, I think, 37 years ago, 38 years ago, and I haven't worked on this very much since. But I was modeling asynchronous circuits, and one of the insights that I had was that asynchronous circuits couldn't control their inputs, right? They took whatever inputs they got from the environment, the signals, electrical signals, and they couldn't stop electrical signals from happening on wires. And so I'd come up with a property called receptiveness, which was a property of regular languages, which I was using to model my circuits. And so I had reduced this to a two-player game. There's the environment, which sends signals to the circuit and actually sees outputs from the circuit, and the circuit itself. The circuits all had input events, capital I, and output events, capital O. And there's an omega regular language that represents the possible behaviors of the circuit. And so for that to be a legitimate representation of a real circuit, it had to have this receptiveness property. And so I made receptiveness into a two-player game where the environmental move could be any string in I star. So it could be the empty string, it could be any length, any series of inputs. And then the circuit had to be able to react to that with a symbol in O. And then basically you concatenate an infinite series of these moves. And for the circuit to be legitimate, the circuit model to be legitimate, there needed to be a strategy that the circuit could execute where we guarantee that the resulting infinite concatenated string is always an L. Now, there are probably people in this room that could have answered this question had I thought to ask them. And if not, they certainly could answer it now. But at the time, I was completely stuck and I didn't know who to talk to. So that turns out to be an instance of Church's problem, which is finding a deterministic finite transducer that is consistent with a finite state recognizer for pairs of input and output symbols, and is important for lots of things, particularly synthesis of implementations of specifications. Anyway, this is a fuzzy picture of the book, which I found to be obscure. I don't know if other people had heard it at this time. I don't know how it was that Alan knew about this book and knew to steer me in this direction. Um, so wrapping up, Alan, I didn't I didn't know Alan that well. I had some very pleasant interactions with him. And of course, I spent a lot of time reading his papers, especially in the 80s. But I found him to be unfailingly kind. And with virtually every sentence that he uttered, I learned something important. Um, and it wasn't until I prepared this talk that I realized how much impact he had on my career, which was my life would have been completely different and probably nowhere near as good without Alan's contributions. So I'm sorry that he's not here to enjoy us praising him, and I know that we'll all miss him. Thank you.
Thank you, David. I really love the memories. So the next speaker is Rajeev Alur. Rajeev, are you on?
Yes.
Yeah, okay, yeah.
But it says I cannot share my video and... Okay, yeah, I guess now I have the permission, yeah.
Okay, do you need a couple of minutes to... Oh yeah, we can see you now, okay.
Yeah.
So Rajeev is a professor at the University of Pennsylvania. So we just heard from David how he wanted to work on the verification of time systems. Well, he finally got his wish. So Rajeev and David together wrote this very influential paper on timed automata, and that's created a whole new branch of research, I would say. And Rajeev is, of course, known for his many other contributions to the theory of program verification. So Rajeev, it's all yours.
Yeah, thank you, Kedar, and yeah, thank you for organizing this event. Yeah, indeed, I'm very sad that Alan is no longer with us, but I will always cherish his memory. And this talk, well, it's titled Automata, Temporal Logics, and New Calculus, because these are the topics that I know Alan was very fond of on the theoretical side of model checking, and he was instrumental in getting me interested in these topics. I'm sorry I cannot be there in person, but I'm hoping to share a few thoughts and few results in memory of Alan. So yeah, actually Dave gave the previous talk, and I joined Stanford as a PhD student in 1987, the same year as Dave joined there as a faculty member. But when I joined, I was, in fact, I didn't know anything about model checking. I was really interested in theoretical computer science. At that time, it was the part of theory that was called Theory B. And as this volume of Handbook of Theoretical Computer Science says, the volume B was on formal models and semantics. This appeared, I think, in 1990, but when I started as a PhD student at Stanford, I didn't know much about research, and I was talking with Zohar Mana, and I said, I'm interested in logic and semantics and theoretical aspects in that general space. So he gave me chapters of this handbook, which it hadn't actually appeared, but Zohar had preprints of some of these, and that's how I started learning about computer science. And one of the chapters that Zohar gave me, and that kind of shaped my career, was this. It's called Temporal and Modal Logic, written by Alan. And I don't know if you can read the table of contents here of this chapter, but it's about well, linear temporal logics, branching temporal logic, then a whole taxonomy relation to fixed point logics like mu calculus and potential research problems in this space. And I read this chapter very carefully. It's very dense, lots of interesting results, beautiful theory, and that's what got me excited about this whole field. And in this symposium, we are hearing a lot about model checking, but I was interested more on the theoretical foundations, particularly understanding temporal and fixed point logics from the lens of expressiveness and the complexity of various decision problems, and how these decision problems could be solved by using automata as a building block, as a unifying procedure. And in fact, Dave told us about this problem about receptiveness in the last, in his talk, and that could be actually solved by as a synthesis problem and using tree automata based decision procedures. And that's how I got excited about this whole area. And this love for the theory that at times contributes to model checking, though I agree with the way Ken described the field, where the general problem is how to verify properties of programs, and for this many tools are relevant, but some contribution also comes from these theoretical insights, and that's what that has been my first love for computer science, and it has remained so till now. And the first time I met Alan was actually at this workshop. So in 1991, summer 1991, by that time I was actually about to finish my PhD, and my thesis was on real-time temporal logics and timed automata. And it was mostly a theoretical PhD trying to understand complexity of various decision problems. And at that time, Willem Paul de Roer, who was a research, established researcher in formal verification, had organized this workshop in this very nice location called MOOC in the Netherlands. And it was like a 4-day workshop, and the topic of the workshop was real-time theory and practice, though in retrospect, practice would be like overselling it. It was more like a theory of real-time with a lot of people with different tools for analyzing time systems, people working in process algebras, which was very popular in Europe in those days, people looking at temporal logics and automata theoretic decision procedures. So that's that was kind of the pool of participants. And I had met Alan before at some conference, I think at CAV in 1990, but this was a meeting where the number of participants was much smaller, and I got to know him well. And at that time, actually, he was also working on extension of CTL and CTL model checking to timed systems, and he had defined a logic called RTCTL. In fact, in this volume, there is a paper by Alan and one of his students on this temporal logic called RTCTL. And in my thesis, actually working with Dave, we had introduced a version of CTL called timed CTL, which we call TCTL. And the big debate at this meeting was, or should the time be discrete, or should it be dense? Dense meaning as in real numbers, or in terms of theory, it turns out whether you take real numbers as the underlying time domain or any dense domain, the basic complexity and the insights are the same. But for discrete, the decision procedures and the tools are very different. And this RTCTL was had the discrete time semantics, whereas the work that I had done in my thesis had dense time semantics, and it required kind of newer procedures. And Alan was appreciative of those newer techniques, but was kind of insistent that discrete time is good enough in practice, and I had to defend and explain why the dense time was still useful, or what were the technical differences. And it was very in a friendly manner, but it was a debate, and I don't know if I convinced him eventually, but since then, he treated me as, even though I wasn't his student, he treated me with great love and always offered me advice and mentorship. And I don't know, must have written lots of letters for me. And I would always appreciate his advice and his insights. And I met him at many, many conferences since then. So going back to this theme of his work, the theoretical part of his work, which was to connect tree automata with mu calculus and branching time logics. Even now, once in a while, I go back to those themes, and let me tell you briefly, like in 5 minutes, one of my recent papers with now my own students, Caleb Stanford, who is now a professor at UC Davis, and Chris Watson, who is a PhD student at Penn. And a couple of years ago, we had a paper in Popple, which was a robust theory of series parallel graphs. So I'll tell you a bit why we are looking at it and its connection to automata and fixed point logics. So we were looking at stream processing systems and how data gets processed in that and what's the underlying semantics. So in stream processing, you get a sequence of data items and you produce a sequence of data items, and a natural way to give semantics to any operator in this stream processing system would be a monotonic function from sequences over input types to sequences over output types, right? But this had some limitations because if the operators many times are derived from relational query operators like in SQL and so on, where if you think about like select or join, the input stream is now viewed as a relation, and there it's not a sequence, so there are lots of opportunities for parallelization. But how to do it correctly, how to parallelize correctly becomes a problem if you're thinking of the stream as a sequence. And in reality, the input stream actually could consist of events happening at multiple places in a distributed system. And so to then to turn it into a sequence then requires enforcing some consistent ordering constraints, and that puts, again, limitations. So this has actually been observed in other places. And so people have been thinking about, can we think of these operators, the streams beyond linear sequences? And a unifying framework for this is to think of these streams as labeled series parallel graphs. And then operators could be viewed as monotonic transformers over these. And let me just illustrate this using a simple example. So suppose we are getting events from different taxis. So in this picture, I have like events coming from a yellow taxi and events coming from a purple taxi. And let's assume that these events give us like when a ride begins, when a ride ends, and maybe some information about the location of the taxi. So we could now think of the input as a partially ordered set where the events of the same taxi are linearly ordered, but the events of different taxis are unordered, except maybe at the end of the day, it's a synchronization because all taxis exchange some information, and those now turn to be synchronizing points. Then you can think of then this input by as this picture shows. So these starts are end of day events, and in between two end of day events have multiple linear sequences. In fact, these lines themselves are unordered, and it could be an arbitrarily many set of taxis. But for each colored taxi, then I have a sequence of events, and the individual events could be about begin right, end right. Now, if you just stare at this picture, then this reminds you of a series parallel graph. So the input itself is the series parallel graphs where vertices are connected using linear sequential composition and parallel composition. And so that's kind of defines these series parallel graphs. There's the specific version that we have, they are called synchronized series parallel graphs. So in the base case, you have a vertex. You can take two graphs, you can connect them, the sink of one with the source of the other, and that's sequential composition. This can be ordered composition, where you take two graphs, you connect them by a source and a target, and From the new source to the to target, you also had the synchronization edge along which information could be passed. And there is also unranked, unordered parallel composition, like was the case in the example of taxis. So I have set of these graphs which can be now combined together using this unordered composition and this synchronization edge, which plays a crucial role in a lot of decision problems and expressiveness results, connects directly the new source with the new target. So these are our synchronized series parallel graphs, which is a class of directed acyclic graphs. And then the question that we asked is, how can we develop a theory of regular languages over these SSPGs, where we want to define automata, maybe temporal logics, get nice expressiveness results, good decision procedures. So the first step towards that is try to define automata. And so in fact, going back to work on automata over trees, some of which was done by Alan, that gives us some starting point over this. And I'm not going to go through the definitions of this automata because we don't have time, but I do have some slides over this. But the properties that we were looking for was it should be equivalent to the monadic second-order logic over such graphs. And these languages should be closed under Boolean operations, determinization, decidable emptiness, and equivalence. And the reason for me to bring these up here is that these are the things that I read for the first time from the survey on the temporal and modal logics, the chapter I showed you at the beginning of this talk. So there is a definition of these automata, and some of these are kind of natural, some of them require some some special care. In particularly, the main thing is that these automata have finitely many states, and a run of this automaton over this complex structure, this series parallel graph, is labeling of the vertices of this graph with automaton states. And the key definition, the key aspect of the transition function is that the label, the state labeling a vertex should be determined based on the states labeling its predecessors. And the only kind of non-trivial case where you have to think a bit about is what happens when you have an arbitrary number of predecessors, which is what happens in an unordered join. And it turns out the right answer is that, let's say if I have two states Q1 and Q2, then maybe the state labeling this join vertex depends on how many states do I have in state Q1 and how many states I have in state Q2 for my predecessors. But we can count only up to some fixed constant because I need a finitary representation of transition function. So the natural set of constraints are, I could say that I have at most 2 states in Q1 and at least 3 states in Q2, right? So then this number 3 becomes kind of the counting complexity of this transition function. So then we went on and studied different properties, which ones are regular properties, and I'm going to skip this, but here is kind of a summary of the expressiveness results that you could define a notion of regularity using deterministic version, and these languages are closed under natural operations like union, intersection. You can define determinization, so you can translate non-deterministic automata to deterministic automata. So typically in the determinization, you think about what's the blow up in states. So here it turns out there is another parameter that counting complexity, that at this unordered join, to what number do I have to count? And an interesting expressiveness result is that for the deterministic automata, the expressiveness increases with count, but for non-deterministic ones, a count of 2 suffices. And this also can be characterized, the same class of these regular languages over these particular class of series parallel graphs can be equivalently characterized by MSO and graded mu calculus. So let me skip this. But the graded mu calculus, against mu calculus is what Alan had worked a lot on, and I learned about it from him. So you have propositions for state labels, and you have least and greatest fixed points, Boolean connectives. But in standard mu calculus, you say that, okay, if A is my label on an edge, you could say that diamond A or box A phi. So these are the kinds of properties. Diamond A phi would mean some successor satisfies phi. In graded mu calculus, you could say in triangular brackets, n comma a phi means that n a successors satisfy phi. So you have some counting also, and now that counting actually relates to the number of that's what we saw in the definition of transition function of the automata. So everything works out actually quite nicely. And this graded mu calculus was introduced by Janine and Lindsay, and we could show actually that this graded mu calculus captures exactly the regular languages of these SS, with this synchronized series parallel graphs. And this is kind of analogous to the work that Alan had done on mu calculus and tree automata and MSO. So with that, let me end here. So he was the one who kind of introduced me to this beautiful world of automata, temporal logics, and mu calculus, and mentored me over the years. And I'm very much thankful to Alan for that, and my love for this theoretical foundations of model checkings continues. Thank you.
Thank you, Rajeev, for those memories and for this really interesting introduction to your work on new automata. So now we have a break for about 20 minutes until 2:10. So what I've been asked to say is, please, when you come back, just sort of squeeze in, because we have many more people coming in after the break. And there's a lot of family and friends who are waiting to come in for the next session. So let's thank all the speakers again for this wonderful session.